Section 6.2 explains the relationship between energy, heat, and work, including their definitions and sign conventions. We'll use these concepts to discuss the internal energy of a system. Our learning outcomes add the law of conservation of energy, as well as some depth to the author's learning goals from the previous slide. Let's begin. When discussing energy flows, we talk about the system, which could be a container of reactants and products, and the surroundings, which is everything outside of that container where the reaction is taking place. Then we get a little philosophical by defining the system and the surroundings as the universe. There are three types of systems we'll deal with in chemistry. The first is an open system, which has no cap preventing the flow of chemicals, and no insulating sleeve isolating the flow of energy from what's going on inside the flask. The second system is a closed system, meaning that chemicals are not free to flow to and from the system, but energy, typically in the form of heat, can. An isolated system adds an insulating sleeve to the closed system so that neither matter nor energy can flow in or out of the system. To borrow some terminology from my colleagues in physics, work is the energy resulting from a force acting on an object over a distance. In contrast, heat, or thermal energy, is the flow of energy that results in a temperature change for the system or the surroundings. Both work and heat can be exchanged between the system and the surroundings. This requires us to define our perspective as being either the system or the surroundings so that we can use positive and negative signs to describe the flow of heat and work. In Figure A on the left, the orange square is our system and the surroundings is everything else. The arrow pointing into the system tells us that work is being done on the system. Since energy in the form of work is being done on the system, then the energy of the system increases. So we say that W is positive. This could be like a person pushing on a car. As the car moves, its speed increases, causing it to have kinetic energy from the work done by the person. In Figure B, we see the system is doing the work, so the system is losing energy. The sign of W will be negative as this energy flows into the surroundings. This could be like a moving car coming to an abrupt stop as it hits a garage door. All the kinetic energy from the car is transferred into work energy done on deforming the unfortunate homeowner's garage door. We can use the same conventions for heat transfer. Suppose our system is an ice cube in Figure A. A person holding the ice cube will transfer heat into the ice, causing it to melt. So Q for heat is positive. A system, such as room temperature water placed in a freezer, can release heat to the surroundings, making the sign for heat negative, as in Figure B. In this example, review each of the questions and determine the sign of W or Q for the flow of work or heat, respectively. In the first scenario, the person is doing work on the system, which is the bowling ball. So from the perspective of the bowling ball, W is positive. In the second scenario, we're switching our perspective from the system being the bowling ball to the system being the person. The person is doing work on their surroundings, transferring energy to the surroundings in the process, so W is negative. In the last scenario, no work is being done, so we're talking simply about the flow of heat from the person's sore back to the ice pack. Since heat is flowing into the ice pack, and the ice pack is defined as our system, Q is positive. So far, we've seen that energy can move freely between a system and its surroundings. We can also convert energy from one form to another, much like wind energy can be converted to electrical energy. This leads us to the law of conservation of energy, which states that energy cannot be created or destroyed, just transferred from one form to another. So think about that for a minute. If energy cannot be created, then it must mean that the energy of the universe is constant, a statement known as the first law of thermodynamics. Consider a glass of water sitting on a table. Does this glass of water have any energy? It may not seem so, but the system of the water and the glass does contain energy. We call this energy U, the internal energy of a system, and it is defined as the sum of all kinetic and potential energies of the particles within a system. This includes the motions of the molecules inside the system. This also includes motions of all the atoms and subatomic particles within the molecules. For this reason, absolute values of U are difficult to determine. But that's okay, because we're more concerned with the changes in internal energy than the total internal energy of a system anyway. Chemists use the Greek letter delta to denote change. Here we see the change in internal energy, delta U, is defined as the final internal energy minus the initial internal energy. We don't formally quantify the absolute values of the final and initial energies, but rather use them to talk about the relative increase in internal energy that makes U final greater than U initial and delta U positive. Or we can talk about the relative decrease in internal energy when U final is less than U initial, causing delta U to be negative. Most commonly, when we need a value for delta U, we'll calculate it in terms of the heat gained or lost and work done on or by a system, rather than using absolute internal energies. We can quickly see that if the system gains heat and work is done on the system, that delta U will be positive from the two energy inputs. Alternatively, if the system loses heat and the system does work on the surroundings, without a doubt the system will lose internal energy. When the signs of Q and W are mixed, however, we'll need to know the values of each to determine if the internal energy of a system increases or decreases. Let's look at an example. In Figure A, the sign of Q is positive, indicating that heat is flowing into the system. The sign of W is negative, indicating that the system is doing work on the surroundings. If we sum the two quantities, we see the change in internal energy of the system is positive 310 kilojoules. However, if the signs of heat and work are both negative, as in Figure B, this indicates that heat is flowing out of the system and work is being done by the system, so the internal energy of the system decreases by 490 kilojoules, as indicated by the negative number. A reaction in a flask releases 890 joules of heat to the surroundings, and the gas produced does 450 joules of work to push the piston upward. Is this a closed, open, or isolated system? Determine the signs of Q and W. Determine delta U. This is a closed system because the matter is contained. The signs of Q and W are both negative. Delta U equals Q plus W, so delta U equals negative 890 joules plus negative 450 joules. So delta U equals negative 1,340 joules. As always, I'll leave you with the parting thoughts of the authors. Don't forget to let the video finish playing through so that your score transfers to Canvas.